Hello and welcome back. We've been looking at independent events in the first video. So the independent events, the formula is there, and the independent event is a set of events where the previous event has no effect on the second. So if you're flipping coins, for example, rolling dice, they don't have memory, they don't have an effect on each other. So the next example, on a trip through Mitchell, Brandon has determined that the probability of hitting a red light is 0.7. So he says there's a 70% chance I'm going to hit a red light at one of the two lights. He's also determined there's a 0.3 or a 30% probability he'll hear a song from his favorite artist, Taylor Swift. So he's listening to the country channel, and he's finding that Taylor Swift is being played 30% of the time. So determine the probability A. He will get stopped at a red light and not hear a Taylor Swift song. So the first question you ask yourself, you have two events here, a red light occurring, so that's event 1, so the red light, and the second event is hearing Taylor Swift. So you ask yourself, are the events related? And the answer is no. I mean, if every time you hear Taylor Swift and the light changes, people have Taylor Swift queued up all the time so they could hit all the green lights or vice versa. And similarly, when the light turns red or green, it doesn't, all of a sudden your radio doesn't change to a particular song. So they're completely independent of each other. So what we need to do here, we look at what Brandon has provided us for his probabilities. So he has said that 0.7% of a red light. So I'm going to say probability of a red light, so RL, is 0.7. Nice thing with probability, you have a little bit of freedom on what you're naming your variables inside the brackets. The second probability, so there's a 0.3% chance he hears Taylor Swift. So the probability of hearing Taylor Swift is 0.3. So to answer question A, what's the probability he gets stopped at a red light? So that means he's going to hit a red light. So the probability of a red light plus not, okay, so not hear Taylor Swift. So it's really Taylor Swift prime because we don't want to hear her. So Taylor Swift over here, we had said, identified that probability of hearing Taylor Swift is 0.3. If we go TS prime, that's probability of not hearing her. So because we've identified it as independent events, we know that it's going to be the probability of a red light multiplied, because it's independent, the probability of not hearing Taylor Swift. So the red light, that's just from the information we've identified, multiplied by, it's going to be 0.7 because the probability of hearing Taylor Swift was 0.3. So the opposite, or the prime of that, would be 1 minus that. So I can write that in here. Probability of not hearing Taylor Swift is 1 minus 0.3, which is 0.7. And that's where that second 0.7 came from. So for hitting a red light and not hearing Taylor Swift, it's a 0.7 times 0.7, so a 0.49 or 49% probability. So there's a 49% probability you'll hear a red light and not hear Taylor Swift, which still seems fairly large, but it is town of Mitchell, so you never know. B part. What's the probability he will not get stopped at a red light? So not get stopped, so that means red light prime, because that would mean green light, and not hear a Taylor Swift song, so that's also TS prime. So now we are looking at both being the negative or opposite of what we've identified. Still independent events, that hasn't changed. So we are looking at red light now as being 0.3 multiplied by 0.7. That hasn't changed from the previous question. So 0.3, because again, hitting a red light is a 0.7 chance. Not hitting it would be the opposite, 1 minus that, and that's where I got the 0.3 from over here. So when you multiply that through 0.3 times your 0.7, you get the 0.21, or a 21% chance. So there's a 21% chance you'll hit a green light and not hear a Taylor Swift song. So it still doesn't seem like a whole lot of odds. It sounds like you're going to be hearing a lot of Taylor Swift, apparently, when you're driving through Mitchell. All right. What happens when the second event depends on the first outcome of the first event? So conditional probability is the chances event B will occur if we know event A has happened. Event A has occurred. So we want to know what's the chances of event B occurring, so the second event, knowing full well that event A has occurred. So the notation for this, the notation looks like this. And the English statement for that, the probability of event B, given that event A has occurred. All right, so that's how you say that out loud. So P, the vertical bar A, inside probability of event B, given that event A has occurred. The formula for this. Formula is similar, so we're still looking at the probability of A and B occurring. The difference this time is that event B really depends on what happened with A. So the formula, typically I keep it in terms of multiplication. It just seems to be a little bit more comfortable for people to work with. So we're basically looking at what's the probability of A multiplied by the probability of B happening, given that we know A has occurred. So it looks very, very similar to the independent events. And this is still probability of A and B occurring. It can be rewritten into or isolated for the probability of B, given that A has occurred. And we're just playing with some algebra here. Oops, and it's the exact same formula. So the two of them are the two different forms. And that would be probability of A. Okay, so there are your two formulas. So what is an example of this? Sammy's computer sometimes crashes when using Facebook. From research, Sammy found that Facebook will freeze 2.5% of the time when it's used more than 15 minutes. Similarly, she found that the chances of Facebook and the computer crashing together is 1%. If Facebook is frozen on Sammy, what's the probability the computer will crash? So what we need to do here is we need to identify, give the events here a bit of a name. So for example, let's call event A Facebook freezing, and event B computer crash. And what this does, this allows you then to apply the formula from above using A and B. So now we have to decipher what information is provided here. And there's a couple key phrases here. So she found that, and I'm going to skip down to the sentence here, the Facebook and computer together is 1%. The key word therefore there in that sentence is and. So Facebook and the computer crashing is 1%. So what that tells me is that the probability of event A and B occurring is 1%. And I'm going to switch that to a decimal. So that's one key piece of information. If you look at the other statement then, the 2.5%, that's when Facebook will freeze. So we've said that Facebook freezing is right here. So Facebook freezing is event A for us. So probability of event A occurring is 0.25%. So again, dividing 2.5 by 100. So using the formula from above, and it doesn't matter.
Someone come in the office for a message, please.
And it doesn't matter which formula you pick from above. Both are valid. I'll pick the top one for argument's sake. A and B equals probability of A, multiplied by the probability of B given A. So we already know, substituting in, probability of A and B occurring is 0.01. Probability of event A is 0.025. And we're looking for the probability of event B occurring given the day. So we're just going to rearrange this formula to solve. And when you do the rearranging, it's just using your algebra rules from grade 9. And when you punch that through the calculator, 0.01 divided by 0.025, so 0.4 or 40%. So therefore, if Facebook has frozen, so that's something we know has happened. So if Facebook has frozen, so I'm getting that from the 2.5%, okay, given part of the question. Remember, we got the 2.5% from the original part of the question. The Facebook will freeze 2.5% of the time. So if we know Facebook has frozen, there is a 40% chance the computer will crash too. And so we're looking at both events actually happening here. So if we know Facebook, in fact, right in front of Sammy, if she sees Facebook freeze, which is a 2.5% chance, there now becomes a 40% chance the computer is going to lock up or crash as well. All right, so there's an example of dependent events. So I have couple of examples with dependent events that we'll clean up in the final segment.